Picture this. You're standing in a Czech factory in 1935, watching a car that looks like it fell out of a science fiction novel idle quietly in the corner. No radiator, no coolant hoses, no water pump. Just a V8 engine sitting in the rear, cooled entirely by air, running smoother and cooler than anything Detroit had ever built. The American engineers watching this couldn't believe what they were seeing. And honestly, neither can most people today. This is Engine Era, and I spend way too much time thinking about forgotten engineering revolutions that should have changed everything but didn't. If you're someone who loves digging into the mechanical decisions that shaped automotive history and the stories behind the engineers who were decades ahead of their time, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. So let's go back, way back, to 1934. While Ford is still dealing with the overheating disasters of their brand new flathead V8, while Chrysler is hauling around 24 quarts of coolant just to keep their straight eights from melting themselves, and while General Motors is trying to figure out why their cooling systems work perfectly on paper but not so much in a Pennsylvania summer, one engineer in Koprivnice, Czechoslovakia, is sitting at a drafting table quietly dismantling every assumption the automotive world had ever made about keeping an engine alive. His name is Hans Ledwinka, and what he built would haunt Detroit for decades.
Here's the thing about water cooling in 1934. Everyone accepted it, the same way everyone accepts traffic jams. Annoying, expensive, full of failure points, but just kind of the price you pay. Think about what a water-cooled engine system actually demands from you. You've got a radiator up front, a water pump spinning constantly, a thermostat that makes life or death decisions every second, rubber hoses that hate heat and cold equally, and somewhere between 16 and 24 quarts of coolant that freezes in winter, boils in summer, and needs to be changed every couple of years. The whole cooling system adds roughly 80 pounds to the vehicle, and every single one of those components is a potential failure point waiting to happen. Now, here's what most people don't realize about why water cooling dominated so completely. It wasn't just tradition. The physics seemed to demand it. Water has a specific heat capacity of 1.0 BTU per pound per degree Fahrenheit. Air, 0.24. Air is literally 4 times worse at absorbing heat than water is. When you're trying to manage the 225,000 BTUs per hour that a 75 horsepower engine produces in waste heat, that gap feels impossible to overcome. The math said air cooling couldn't scale beyond motorcycle engines. Every thermodynamics textbook of the era basically told you the same thing. Use water, full stop. Ledwinka read those textbooks too. He just disagreed with the conclusion. See, Ledwinka had been designing air-cooled engines at Tatra since 1923. He started with flat twins, moved to flat fours, and spent a decade learning something that nobody else in the industry was paying attention to. The question wasn't about the cooling medium at all. Everyone was asking, how do we move heat from the engine into the coolant efficiently? Ledwinka flipped it completely. He asked, what if we designed the heat transfer interface itself to be so effective that the medium didn't matter?
That reframing, that single shift in perspective, is what made everything else possible. When he sat down to design the engine for the Tatra 77 in 1933, he started with a blank sheet and a radical premise. Don't try to make air behave like water. Design an engine specifically, intentionally, and obsessively for air cooling from the very first line on the page. Every surface, every fin, every airflow channel would be calculated and optimized before a single piece of metal was cut. What came out of that process was the Tatra 77's 2,970cc V8, about 181 cubic inches in American terms. The cylinders were arranged at 90 degrees, which sounds familiar until you realize that everything else about this engine was utterly alien to Detroit. Each cylinder was an individual aluminum casting, not a bank, not a block, not a shared structure, individual. And each one was covered in precisely engineered cooling fins that Ledwinka had calculated down to the millimeter. here's where it gets really interesting. Ledwinka discovered through exhaustive testing that fin spacing was the critical variable nobody else was even measuring. Space the fins too close, and you create dead air pockets where heat just sits and builds. Space them too far apart, and you lose surface area. After months of testing, he landed on 4.5 millimeters between fins, each fin 1.5 millimeters thick, extending 30 millimeters out from the cylinder wall. That configuration gave him 287 square inches of cooling surface per cylinder, nearly 3 times what a water jacket offered on a comparable water-cooled unit.
But surface area is only half the equation. You need air moving across that surface, and moving fast. This is where Ledwinka's genius really reveals itself. He designed a centrifugal blower driven directly off the crankshaft at 1.4 times engine speed. At 3,000 RPM, that blower was spinning at 4,200 RPM and moving 2,100 cubic feet of air per minute through a system of carefully shaped metal shrouds that created a Venturi effect, accelerating airflow precisely where temperatures peaked. Around the exhaust valve areas, temperatures could hit 1,400 degrees Fahrenheit. The ducting sent the strongest airflow right there first. The spent hot air exited through louvers in the engine compartment floor, which created a natural convection current pulling fresh, cool air in through the upper grills. The car itself was part of the cooling system. The aerodynamic body, which achieved a drag coefficient of 0.36 when most cars were pushing 0.7, created specific pressure zones that enhanced airflow through the engine bay. The belly pan wasn't just aerodynamics, it was a cooling exhaust strategy. Every piece of the design talked to every other piece. Now, you might be thinking, okay, but did it actually work? Like in the real world, under load, in actual conditions? This is the part that broke the Chrysler engineers.
When Fred Zeder's team arrived at the Tatra factory in early 1935, they spent 3 days going through every piece of test data Tatra had. They drove a Tatra 77 on the factory test track and pushed it as hard as they could, looking for the thermal breaking point they were certain existed. They never found it. The dynamometer data showed cylinder head temperatures stabilizing at 428 degrees Fahrenheit under full load. Comparable water-cooled engines of the era were regularly hitting 450 degrees or higher under stress. Oil temperatures never exceeded 248 degrees. And here's the number that really got them. Only a 15-degree variation between the hottest and coolest cylinders. Water-cooled V8s of the time showed variations of 40 degrees or more. Ledwinka's air-cooled engine was more thermally consistent than the technology that was supposedly superior to it. The Chrysler team came back to Detroit with their findings, and their conclusion was essentially, yes, it works, but we can't afford to care. And that answer, that very human, very understandable business answer, is how one of the most important engineering breakthroughs of the 20th century got quietly buried. Retooling for air-cooled engine production in 1935 would have cost Chrysler an estimated $12 million. In today's money, that's roughly $260 million. For a technology that customers weren't asking for, that required completely rethinking vehicle architecture, that demanded manufacturing capabilities American factories simply didn't have. Every cylinder needing to be individually cast with precisely controlled fins. Blower and ducting systems requiring sheet metal work outside of anything on the factory floor. A rear-mounted engine layout that would have forced a complete redesign of the entire vehicle platform. Water cooling worked well enough. Why blow up the entire operation for something the buying public didn't even know they wanted? And that's a completely rational business decision. It really is. But rational business decisions have a funny habit of leaving the most important ideas on the table. Here's the thing about Ledwinka's engine that went beyond just the cooling solution. He wasn't fixing one problem. He was solving a cluster of interconnected problems simultaneously, and that's what makes his work so extraordinary. The complete Tatra V8 with its cooling system weighed 364 pounds. A comparable American water-cooled engine, including its radiator, pump, hoses, and coolant, came in around 80 pounds heavier. That's not a rounding error. That's a meaningful performance advantage, and it came off the rear of the car, which improved the weight distribution for handling. No radiator blocking the nose of the vehicle meant the streamlined body could do what Ledwinka had designed it to do aerodynamically. No water pump meant one less rotating assembly to seize. No hoses meant no burst hoses. No antifreeze meant no freeze-ups in Czech winters, and no boilovers in Egyptian summers. And before you think Egyptian summers are an edge case, consider this. In 1935, a Tatra 77 was driven from Prague to Egypt and back, 7,000 miles through conditions that routinely killed other cars. Temperatures exceeding 120 degrees Fahrenheit in the desert sections. While other vehicles in the same region were constantly pulling over to refill radiators, let temperatures drop, fix overheating-related failures, the Tatra kept moving. The driver's report noted that the only maintenance required during the entire journey was adding approximately 1 quart of oil every 1,000 miles. That's it. That's the maintenance log for a 7,000-mile round trip through some of the harshest conditions a car could face.
The durability numbers from Tatra's own testing backed this up. Engines were regularly achieving 100,000 kilometers, around 62,000 miles, without major repairs. In the 1930s, when most engines needed a complete rebuild by 30,000 miles, that number sounds fictional. But it makes sense when you understand the mechanism. Water-cooled engines experience significant thermal cycling. They run cold at startup, heat up rapidly, and oscillate with load changes. That constant expansion and contraction stresses gaskets, cylinder bores, bearing surfaces, and every seal in the system. Ledwinka's engine, because of its superior thermal consistency, ran at a more stable temperature throughout its operating range. Less thermal cycling meant less mechanical stress over time. Less stress meant longer component life. The physics pointed directly at the durability numbers. Let's talk about the metallurgy, because this is where Ledwinka's obsession with getting every detail right becomes almost uncomfortable to look at. The aluminum cylinder heads used a special alloy with 4% copper content, specifically chosen for improved thermal conductivity. The cast iron cylinder liners were centrifugally cast for uniform wall thickness, then machined to exact tolerances. The steel cooling fins were furnace brazed to the cylinders in a process that took 14 hours per cylinder. 14 hours per cylinder for an 8-cylinder engine. That's 112 hours of brazing time just for the fins, because Ledwinka knew that a poor thermal bond between the fin and the cylinder wall would undermine every other calculation he had made. The interface had to be perfect, or nothing else mattered. The valve tree reflected the same level of thinking. Overhead valves, operated by push rods from a single camshaft sitting in the valley between the cylinder banks. Compact, effective, and cleverly positioned so the valves themselves were exposed to the cooling airflow. This prevented the valve spring weakening that plagued many engines of the era, where springs would lose tension from sustained heat exposure and cause valve timing issues that compounded into larger failures. Ledwinka had thought about that failure mode and designed it out. Cold weather starting was another problem he addressed directly. A manual advanced magneto ignition allowed optimal timing for starting, then advanced for running conditions. The intake manifold used exhaust heat to warm incoming air during the first minutes of operation, preventing carburetor icing. Within 2 minutes of starting, even in genuinely sub-zero temperatures, the engine reached operating temperature. Most water-cooled engines of the era took significantly longer to warm up because the coolant itself had to absorb heat before it could transfer it to the thermostat and begin managing temperature properly. Ledwinka's system heated the components that needed heat directly, without intermediaries.
The quality control process at Tatra reflected the seriousness with which they treated the engineering. Each engine was assembled entirely by a single technician, who then signed their name on a plate attached to the crankcase. That technician was personally accountable for the engine's performance. After assembly, every unit ran on a test bench for 4 hours with continuous monitoring of temperatures, pressures, and power output before it was cleared for installation. This wasn't just pride, it was a system of accountability built into the manufacturing process, ensuring that the precision Ledwinka had designed in was actually delivered in every unit that left the factory. Now, you might be thinking, all of this sounds extraordinary, so how did it not take over the world?
How does an engine this far ahead of its time stay a historical footnote while the inferior technology it made look outdated continued to dominate for another half-century? The answer is layered, and each layer is worth examining because together they tell a story about how breakthrough technology actually fails to spread. It's not usually because the technology stops working, it's because the systems surrounding established technology are far more powerful than any single engineering achievement. Start with the industrial reality. Detroit in 1935 had billions of dollars of infrastructure, tooling, supplier relationships, trained workforce, and institutional knowledge all built around water-cooled engine production. Chrysler alone had dozens of facilities producing water pumps, radiators, coolant systems, and related components. Switching to air cooling wasn't just a matter of redesigning the engine, it meant dismantling and rebuilding an entire industrial ecosystem. Every supplier relationship would need to change, every assembly line would need to be retooled, every mechanic in every dealership and independent shop across America would need to learn a fundamentally different system. The cost wasn't just the $12 million in factory retooling, it was the entire interconnected web of manufacturing and service infrastructure built around the technology being displaced.
This is the pattern you see over and over in engineering history. The better solution loses not because it fails technically, but because the worse solution has already won organizationally. The technology that gets there first builds walls around itself made of infrastructure, training, habit, and sunk cost that even significantly superior alternatives struggle to breach. Then there's the political dimension, which is easy to overlook when you're focused on the technical brilliance. By 1938, Czechoslovakia was under enormous pressure from Nazi Germany. Tatra was increasingly directed toward military vehicle production. After the war ended, the communist government that took control had a completely different set of priorities. Advanced luxury automobiles with cutting-edge engineering were viewed as bourgeois excess. Tatra's production shifted toward utilitarian vehicles for party officials and state use. The engineering culture that had produced the 77 and the 87 was essentially dismantled by the political reality surrounding it. Ledwinka himself spent 6 years in a Czechoslovakian prison on collaboration charges that were later proven to be fabricated. He was eventually exonerated, but the damage to his health and to the institutional momentum of his work was permanent. Here's what most people don't realize about the way Ledwinka's ideas actually did spread, just without his name attached to them. Ferdinand Porsche visited Tatra multiple times during the 1930s and took extensive notes. The Volkswagen Beetle's air-cooled flat 4 uses fin spacing and airflow management principles that trace directly back to Ledwinka's methodology. That engine would go on to become the most produced air-cooled automobile engine in history. When you look at the Porsche 911's air-cooled flat 6, you are looking at a direct philosophical descendant of the Tatra V8. The 911 Turbo of the 1970s was producing 260 horsepower from an air-cooled engine. In the same decade, most American engineers still believed that air cooling couldn't scale to high-performance applications. Porsche was proving them wrong using ideas that a Czech engineer had demonstrated way back in 1934.
Chevrolet's Corvair, introduced in 1960, represents perhaps the most interesting American attempt to engage with Ledwinka's legacy. Ed Cole, Chevrolet's chief engineer, had studied the Tatra designs carefully and genuinely believed that air cooling could work in an American production context. The Corvair's air-cooled flat 6 was legitimately innovative. But here is where the industrial pressure that had stopped Chrysler in 1935 showed up again in a different form. Where Ledwinka had used individual cylinder castings specifically because they allowed optimal fin design and airflow management for each cylinder independently, Chevrolet used shared bank castings because they were cheaper and easier to produce at American manufacturing volumes. That compromise introduced the cooling inconsistencies that Ledwinka had specifically designed around. The system worked, but it worked less well than it should have, because the cost pressures of mass production forced the shortcuts that undermined the core engineering. The aviation world is where Ledwinka's influence is most directly measurable and least often acknowledged. Lycoming and Continental,
the two dominant manufacturers of small aircraft engines, both adopted fin spacing and airflow ducting principles that closely mirror Ledwinka's calculations during the 1940s and 1950s. To this day, the vast majority of small general aviation aircraft fly behind air-cooled engines whose thermal management geometry would be recognizable to Ledwinka if he could examine them. Every Cessna 172 that takes off from a small airfield, every Piper Cherokee cruising at 8,000 feet is using principles that a Czech engineer worked out on a drafting table in Koprivnice in 1933. And here's the deepest irony of all. Modern water-cooled engines, the very technology that supposedly made Ledwinka's approach unnecessary, have progressively adopted his fundamental insights as computational fluid dynamics has allowed engineers to actually see what's happening inside their cooling systems. Today's precision-designed cooling passages create specific flow velocities and direct coolant to exact locations with exactly the intentionality that Ledwinka was applying to airflow in 1934. The modern engine, with its computer-optimized cooling jacket geometry, is doing with liquid what Ledwinka did with air. He was working the problem correctly. He just had the wrong medium for an industry that wasn't ready to change everything else to accommodate the right medium.
Modern CFD analysis has been applied retrospectively to Ledwinka's fin geometry and spacing calculations. The results are striking. Working with slide rules, physical intuition, and empirical testing, he arrived at values that modern computational methods confirm were nearly optimal. The 4.5 millimeter fin spacing that he settled on through months of smoke flow testing sits within 5% of what a modern simulation produces as the theoretical optimum for the thermal properties of that aluminum alloy at those operating temperatures. He didn't have the math to prove it. He had the intuition to find it anyway. Let's look at what those Chrysler engineers actually missed during their 3 days at the Tatra factory, because this is the part that makes the story genuinely tragic from an engineering perspective. They evaluated the engine, they reviewed the test data, they drove the car, but they analyzed it as an isolated component rather than as an integrated system. Ledwinka had not designed a cooling system for an engine. He had designed a thermally integrated vehicle. The body shape, the belly pan, the placement of the oil cooler, the angle of the inlet grills, the geometry of the engine compartment, the exit louvers in the floor, every element of the Tatra 77 was part of a single, coherent thermal management solution. The engine's cooling system didn't end at the blower shroud. It extended to the outer skin of the car. When Chrysler's engineers went home and tried to evaluate whether air cooling could work in one of their existing platforms, they were asking the wrong question. They were trying to transplant an organ from one body into another without understanding that the organ was only viable as part of the complete original body. Air cooling done Ledwinka's way required designing the entire vehicle around the cooling philosophy from the very beginning. You couldn't just swap out the engine and the radiator and expect the same results. The whole system had to be conceived together. This is why Chevrolet's Corvair, despite Cole's genuine understanding of and respect for the underlying principles, couldn't fully replicate what Tatra had achieved. The Corvair was an air-cooled engine installed in a vehicle that had to meet American expectations about interior space, luggage capacity, ride comfort, and manufacturing cost. It was a compromise between Ledwinka's integrated philosophy and the practical demands of a mass-market American automobile. And compromises, by definition, give you something in between.
The Tatra 77's complete specifications are worth sitting with for a moment because they tell you something important about what Ledwinka actually achieved relative to the time. The 2,970cc engine used a bore of 75 mm and a stroke of 84 mm, giving it a slightly over-square design that favored higher RPM operation. Compression ratio was 5.6 to 1, which sounds conservative by modern standards, but was entirely appropriate for the fuel octane ratings available in 1934 Czechoslovakia. A single Zenith 36VI carburetor handled fueling duties, though Ledwinka experimented with dual carburetor setups that pushed output to 85 horsepower. The engine used full-pressure lubrication with a gear-type oil pump delivering oil at 42 psi to all bearing surfaces. The crankshaft was fully counterweighted for smooth operation at higher RPM. The connecting rods used floating wrist pins to reduce friction. These were features you expected to find in racing engines.
Ledwinka built them into a production car designed for wealthy Czech businessmen and professionals. The combustion chamber geometry was another element that reflected his systematic thinking. The valves were inclined at 25 degrees to create a semi-hemispherical combustion chamber that improved mixture turbulence and combustion efficiency. This is a design philosophy that wouldn't become mainstream in American passenger car engines until the 1960s, with the spread of true hemispherical and near-hemispherical combustion chamber designs. Ledwinka was applying it to a production vehicle in 1934, not because he was chasing performance numbers, but because it was the thermally optimal solution for his cooling approach. Better combustion efficiency meant less waste heat to manage, which reduced the load on the cooling system, which made the whole integrated solution more robust. The intake manifold deserves particular attention because it represents Ledwinka's empirical methodology at its most impressive. He didn't have access to flow testing equipment beyond what he built himself. He constructed a primitive flow bench using a shop vacuum and a smoke generator, injecting smoke into the manifold and photographing how it distributed to each intake port. Then he would modify the manifold geometry based on what he observed, build a new pattern, and test again. This process repeated dozens of times over months until he had a manifold that delivered consistent mixture distribution to all 8 cylinders. Consistent mixture distribution meant consistent combustion events across all cylinders, which meant consistent heat generation, which meant the cooling system could be designed to a specific and predictable thermal load rather than having to accommodate wide variation. Every element connected back to the central philosophy of thermal management as a system property rather than a component property. The Tatra 87, introduced in 1937, represented Ledwinka's refined second generation of the concept. The engine displaced 2.97 liters, same as the 77, but produced 85 horsepower through improved breathing and a slight compression ratio increase made possible by better fuel quality availability. More significantly, the 87 weighed about 60 pounds less than the 77, despite similar output, reflecting what Ledwinka had learned about removing material from areas where it contributed to weight without contributing to either structural integrity or thermal management. The car itself achieved a drag coefficient of 0.36, remarkable for 1937 and frankly competitive with many modern vehicles. The 87 could achieve a genuine 100 miles per hour in top speed testing, which put it among the fastest production cars available anywhere in the world at that price point.
During World War II, the German Wehrmacht's experience with Tatra's air-cooled engines provided an unintentional field test of extraordinary scope and rigor. German forces used Tatra air-cooled engines in various military vehicles across both the North African campaign and the Eastern Front. The range of conditions these engines encountered across those two theaters was essentially every extreme environment an engine could face: intense dry heat, blowing sand, extreme cold, mud, irregular maintenance intervals, fuel of variable quality. The performance in these conditions contributed to the Wehrmacht's interest in securing Tatra's production capacity and engineering talent, which had consequences for Ledwinka personally after the war ended and accusations of collaboration were leveled against him. After Ledwinka's release from prison in 1951, he spent his final years in Munich, where he was close enough to Porsche's operations to watch his influence play out in real time without ever receiving full acknowledgement for it. The Volkswagen lawsuit that Tatra eventually pursued and settled, with Volkswagen paying compensation for the intellectual property influence on the Beetle's design, was one formal recognition of how far his ideas had traveled. But the deeper influence, the systematic approach to thermal integration, the fin geometry principles, the thinking about cooling as a vehicle-level rather than engine-level problem, spread through the engineering community in the informal way that ideas usually spread. Through engineers who had studied the Tatra designs, who worked at firms that had examined them, who trained other engineers who went on to work on entirely different vehicles in entirely different countries.
Now here's what most people don't realize when they look at the ultimate failure of air cooling in mainstream automotive applications. The reason air cooling lost wasn't that Ledwinka was wrong. The reason air cooling lost was emissions regulations and the need for precise thermal control that catalytic converters and early electronic fuel injection systems demanded in the 1970s. Catalytic converters are highly sensitive to exhaust gas temperature. Too cold and they don't light off and convert pollutants efficiently. Too hot and the catalyst material degrades rapidly. Managing exhaust temperature precisely requires managing combustion temperature precisely, which requires managing coolant temperature precisely in a way that water cooling with electronic thermostats handles more easily than air cooling with mechanical fan speed control. Early electronic fuel injection systems similarly benefited from the more stable and controllable thermal environment that liquid cooling provided as computers started managing engine behavior. In other words, air cooling didn't fail because the physics stopped working. It failed because the regulatory and technological context changed in ways that favored the more easily controlled thermal environment of liquid cooling. If Ledwinka had been designing in an era of computer-controlled variable speed cooling fans and electronic temperature monitoring, the calculation might have come out differently. The technology that beat his approach wasn't simply better. It was better suited to a specific set of external requirements that nobody could have predicted in 1934.
This distinction matters beyond automotive history. It shows up in how we evaluate engineering decisions generally. We tend to look at which technology won and work backward to construct a narrative about why it deserved to win. But the reality of technological competition is messier and more contingent than that. Technologies win because they fit the institutional, regulatory, economic, and cultural context of their moment, not simply because they are superior along the dimensions that matter most to engineers. Ledwinka's air-cooled V8 was superior on several dimensions that should have mattered enormously: weight, reliability, maintenance simplicity, durability, thermal consistency. It lost anyway because the dimensions it was superior on weren't the ones that determined industrial adoption decisions in 1935 America. Understanding this has practical implications for how we think about technology adoption today. When we look at why certain genuinely superior technologies fail to achieve market penetration while inferior alternatives dominate, the answer is almost never simply that people are irrational or that corporations are malicious. The answer is usually that adoption decisions are made within a complex web of institutional, economic, and regulatory constraints that can make the technically superior choice the practically inferior choice for any specific actor at any specific moment. Chrysler's decision not to adopt Ledwinka's technology was correct given their constraints. It was also wrong for the industry as a whole and wrong for the eventual trajectory of engine technology. Both of those things can be true simultaneously.
Let's look at the 255 cars that actually got built, because what happens to them tells you something interesting about how history reassesses engineering significance. Between 1934 and 1938, Tatra produced 255 units of the 77. At the time they were sold, their price of 75,000 Czech crowns, roughly equivalent to $60,000 in today's purchasing power, limited their audience to the wealthiest tier of Czech society. Government officials, industrial executives, a handful of progressive engineers who could actually appreciate what they were buying. The cars were well regarded, but not celebrated in the way that, say, a Bugatti or a Mercedes of the same era attracted attention and coverage in the international automotive press. Today, surviving Tatra 77s and 87s trade at prices well into seven figures when they come to market, which happens rarely. The reason isn't simply scarcity, though 255 units with a survival rate affected by a world war and 40 years of communist governance is genuinely rare. The reason is that people who understand automotive engineering history recognize these cars as primary documents of a road not taken. Driving a Tatra 77 is as close as you can get to experiencing what the 1930s automotive world might have looked like if the industry had chosen differently. The rear weight bias, the absence of engine noise from ahead of you, the extraordinary aerodynamic stability at speed, the mechanical soundtrack of the air-cooled V8 that sounds unlike any other engine of its era. These are not just historical curiosities. They are data points in an alternative history of transportation that almost happened.
When you hear a Tatra V8 running, what strikes you is the quality of the mechanical sound.
It's more purposeful than an American V8 of the same period, crisper, more defined. There's a reason for this. The individual cylinder castings eliminate the shared structure resonances that give water-cooled engines of the era their characteristic low-frequency rumble. Each cylinder is acoustically isolated from the others, so what you hear is 8 individual combustion events rather than the blurred combined resonance of a shared block structure. Ledwinka wasn't thinking about acoustic signature when he made the design choices that produced this sound. He was thinking about thermal management and manufacturing precision, but the sound is a byproduct of getting those things right. The lubrication system deserves more attention than it typically receives in discussions of the Tatra V8, because it's another area where Ledwinka's insistence on racing engine technology in a production context paid long-term dividends. The gear-type pump delivering 42 psi to all bearing surfaces was significantly more robust than the splash lubrication and partial pressure systems common in many American engines of the 1930s. The full-pressure system meant bearings were consistently lubricated across all operating conditions and RPM ranges, which contributed directly to the engine longevity that Tatra's testing demonstrated. It also meant the engine could tolerate higher operating temperatures without oil film breakdown at the bearings, which gave Ledwinka additional thermal headroom in his cooling calculations. Every design decision he made created headroom for every other decision.
This is what sophisticated, integrated engineering actually looks like. It's not about any single brilliant solution. It's about a system of decisions where each element reinforces the others, and the whole performs significantly better than a collection of individually optimized components would. Ledwinka understood this at an intuitive level before systems engineering existed as a formal discipline. He was practicing it by instinct and experience while Detroit was still optimizing components independently and hoping the assembled result would behave well. The legacy conversation usually focuses on Porsche and Volkswagen, and that's appropriate because those are the most commercially significant downstream applications of Ledwinka's principles. But there's a less discussed influence worth examining. American military engine development in the 1950s and 60s made extensive use of air-cooled technology for applications where the absence of a liquid cooling system that could be punctured by weapons fire was a meaningful tactical advantage. The Continental AOS 895 used in the M113 armored personnel carrier and the Lycoming LTC-4 turboshaft used in various helicopter applications both reflect engineering decisions shaped partly by the demonstrated viability of air cooling in demanding conditions. Tatra's wartime performance had contributed to this institutional knowledge in ways that were filtered through German military engineering records that became available to Allied engineers after 1945. The turbine engine world is a different conversation, but it's worth noting that all gas turbine engines are technically air-cooled in the sense that airflow through the engine performs the cooling function. The engineering challenges are different at turbine operating temperatures and pressures, but the fundamental insight that Ledwinka applied, design the heat transfer interface first and optimize the flow path second, is structurally identical to how modern turbine cooling design works. Modern turbine blades, with their internal cooling channels and thermal barrier coatings, are solving the same basic problem Ledwinka solved with his fin geometry. The problem has gotten harder and the solutions more sophisticated, but the framing of the problem hasn't changed. What Ledwinka gives us, ultimately, is a case study in what happens when an engineer refuses to accept a conventional framing of a problem. The conventional framing in 1933 was, engines need water cooling. The engineering challenge is to make water cooling work better. Ledwinka's framing was, engines need heat rejection. The engineering challenge is to design the most effective heat rejection system possible, and then figure out what medium makes sense. Starting from the second framing rather than the first is what made everything else possible. It's also what made his solution unintelligible to engineers who had spent their careers optimizing within the first framing. They could see that it worked. They couldn't see how to build their next generation of cars around it, because their next generation of cars was already conceptualized within a framework where water cooling was an axiom rather than a variable. The 1960 Corvair situation is worth one more look because it contains a lesson that extends well beyond automotive history. When Ralph Nader published his criticism of the Corvair in 1965, the air-cooled engine was one of several technical choices that came under scrutiny, though the handling characteristics and fuel system design received the most attention. The subsequent congressional hearings and the broader consumer safety movement they catalyzed contributed to the regulatory environment that would ultimately make air cooling untenable for emissions-controlled engines in the 1970s. There's a painful irony here. The most serious American attempt to bring Ledwinka's philosophy into mainstream production became one of the catalysts for the regulatory changes that closed the window on air cooling entirely. The Corvair's compromised execution of air-cooled principles contributed to an outcome that foreclosed the possibility of a better executed air-cooled design achieving market success in America. This is the kind of contingent, interconnected causality that makes technology history genuinely difficult to reason about cleanly. We want to identify the key decision point where everything could have gone differently, but usually what we find instead is a web of decisions, compromises, accidents, and contextual forces where changing any single node would have changed others in unpredictable ways. Ledwinka's technology might have succeeded in America if Chrysler had adopted it in 1935. Or it might have been compromised by the same manufacturing cost pressures that undermined the Corvair, producing an outcome that damaged the reputation of air cooling rather than establishing it. We can't know because the path that was actually taken foreclosed all the alternatives.
What we can say with confidence is that Hans Ledwinka's air-cooled V8 represented a level of integrated systems thinking that was genuinely ahead of its time, demonstrated by the fact that it took the rest of the engineering world decades to independently arrive at principles he had implemented in 1934. The fin spacing calculations, the integrated vehicle-level thermal management, the emphasis on thermal consistency across all cylinders, the combination of racing engine mechanical sophistication with production car durability expectations, these were not just clever solutions to 1930s problems. They were a demonstration of an engineering methodology that produces better outcomes than component-by-component optimization. Ferdinand Porsche understood this better than anyone. His repeated visits to Tatra were not just reconnaissance missions to gather competitive intelligence. They were study sessions with an engineer he recognized as working at a fundamentally different level. The note-taking was the behavior of a student, not a competitor. And when Porsche went on to create the vehicles that would carry his name to global recognition, the student's fingerprints were everywhere. The rear engine layout, the air-cooled philosophy, the insistence on thermal integration as a system design principle rather than an afterthought, these are Ledwinka's ideas in Porsche's execution.
The question of credit is complicated by the Tatra lawsuit settlement, by the political disruptions of the wartime and post-war period, and by the fact that Ledwinka spent 6 years in prison during the years when his influence was being most actively absorbed and implemented by others who were operating in free market environments where they could commercially develop what they had learned. He was vindicated legally and professionally, but vindication came too late and in too limited a form to restore his place in the public narrative of automotive engineering history. Here's what this story asks us to think about as we watch our current moment of automotive disruption play out. Electric vehicle technology is doing to internal combustion what Ledwinka did to water cooling orthodoxy. It's not asking how to make the existing approach better. It's asking whether the existing approach is the right framing of the problem at all. The engineers at established manufacturers who are responding to this challenge with incremental improvements to internal combustion technology while simultaneously pursuing electric development are in exactly the position of Chrysler's engineers in 1935. They can see the alternative clearly, they understand that it works, and they are constrained by the same institutional, economic, and infrastructural forces that kept Chrysler from acting on what they found in Koprivnica.
Some of those manufacturers will make the transition successfully. Others will be the water-cooled V8 manufacturers of 2035, technically competent, but institutionally unable to move fast enough. The pattern is not new. Ledwinka showed us the pattern 90 years ago. The engineers who were willing to question whether water was actually necessary for engine cooling were the ones who created the most enduring solutions. The engineers who accepted water cooling as an axiom and optimized within it produced good work, but work that was bounded by a constraint that didn't have to exist. The surviving Tatra 77s and 87s that appear occasionally at major concours events aren't just beautiful old cars. They're physical arguments. Arguments that the engineering establishment's consensus can be wrong. Arguments that the outsider with the radical idea and the rigor to implement it correctly deserves more than a 3-day visit and a polite report concluding that the tooling costs are prohibitive. Arguments that the path you didn't take might have led somewhere better, and that understanding why you didn't take it is as important as celebrating the path you did. When you watch one of those Tatras fire up and settle into its distinctive air-cooled idle, listen carefully. That mechanical, purposeful sound is not nostalgia. It's a question. It's asking whether the engineers of 1935 made the right choice, and whether the engineers of today are making the same kind of choice for the same kind of reasons, and whether 90 years from now someone will be making a video about the brilliant technology that existed right now that the industry couldn't afford to adopt because the sunk costs were too deep and the institutional inertia was too strong.
Hans Ledwinka died in 1967. Exonerated but not celebrated. Influential but not credited. His engine died with the last Tatra V8 production run in 1975. But the thinking that produced it is very much alive. In every Porsche Flat 6 that ever turned a lap at the Nürburgring. In every small aircraft that has taken off behind a Lycoming 4-cylinder since 1950. In every modern engine with its precision cooling passages designed by CFD software to do with liquid what Ledwinka did with air by instinct and empirical testing in 1933. The question he asked, why are we accepting this constraint, is the most important question in engineering. It's the question that produces the breakthroughs. It's the question that makes the establishment uncomfortable, because it implies that the consensus might be wrong, and that the person asking might be right. Ledwinka was right. The establishment was rational. And somehow both of those things being true simultaneously produced one of automotive history's most instructive and melancholy stories. What's the most innovative engine design you've ever come across? Drop it in the comments. Let's talk about the engineers who asked why, and the answers they found that nobody was ready to hear. And if this kind of deep dive into the engineering decisions that shaped and sometimes failed to shape the world is what you come here for, make sure you're subscribed, because there are more stories like this one, and every single one of them has something to teach us about how we make decisions about technology today.